Hello everyone, welcome to our channel. Let us solve fracture questions. In the Griffith equation, the fracture stress is proportional to. If you see the Griffith equation, that is sigma f equal to 2e gamma s upon pi c with power half. So see here, c is the crack length, right? So sigma f will be directly proportional to 1 by root over c. So option B, right? So if it is an internal crack, then this will be 2c, right? So we take half of this. But suppose it is a surface crack, then we take it as c. Okay. Next, the fracture strength of a borosilicate glass where gamma, that is yield, this is your Young's modulus, y, it is 65 giganewton per meter square, and surface energy is 0.5 joule per meter square, with a surface crack of 1 micrometer deep and with the crack faces parallel to the tensile axis. Okay, so here there is a sample and there is a crack such that it is parallel to your tensile axis. Suppose this is your tensile axis and it is parallel. So guys, once this crack is parallel, then this crack is not prone to cracking, right? But if this crack is perpendicular, then it is prone to cracking, right? So this presence of crack in the parallel direction will not hamper any property, right? So this will just behave like a normal material without any kind of defects, right? So in that case, the fracture strength, if we calculate for a material which does not contain any defect, then it comes around your 1 by 6 times of elastic modulus. So this is your option C, right? So this is a tricky question. Okay, now suppose this crack would have been perpendicular to this line, then you must have used the formula which we know to find the fracture strength, right? So then the answer would have been there, but here the crack is along the tensile axis, so that's why it will not be valid. Okay, let us proceed. If the surface crack causing fracture in a brittle material is made twice as deep, the fracture strength will be, right? So this is also based on this formula 2e gamma s by pi c. So this is first case, right? So let us take the second case where we make the surface crack twice, right? So it will be 2e gamma s by pi 2c power half, right? So if we divide both from here, so it will be like if you can divide this, so 2e gamma s by pi c, 2e gamma s by 2 pi c, right? Root 2, right? So here it is asking if the surface crack is made twice. So sigma f dash is equal to sigma f by root 2. That means the fracture stress decreases, right? As we increase the crack size, the fracture stress decreases. This is logical also. Okay, so this decreases by a factor 1 by root 2. Okay, next, a silicate glass has a relatively lower fracture strength because here it telling you that it has a lower fracture strength. Why? The Young's modulus of glass is low, right? It doesn't, represent correctly, the Young modulus of glass is low. The cracks propagate before Griffith criterion is satisfied. Now, the crack should propagate only once the Griffith criterion is satisfied, right? Plastic deformation during crack propagation causes fracture. No, plastic deformation during crack propagation it does not allow the crack to grow. So it is a contradictory statement. Option D. The cracks are sharp and propagate as soon as Griffith condition is met. Yes. So this is your right answer. The cracks are sharp, right? Suppose this is sharp crack and propagate as soon as Griffith condition is met, right? So this is the correct one. In brittle materials with atomically sharp cracks, the stress concentration at the tip of the crack is a factor of atomically sharp. That means it is very sharp, just by the gap of atom, right? Suppose. Okay. So once it is there, right? So if you see the formula which is given in the V-Raman book, then the sigma max, that is concentration, stress concentration, is given by the formula C by rho. C is the crack length, rho is the radius of curvature. Okay. So for the case of this atomically sharp crack, this crack length is of the order of 1 micrometer and this radius is order of 1 angstrom. This is of 1 angstrom. So now if you put this value, it is 2 sigma, say 10 power minus 6, here 10 power minus 10. Right? So it will be 2 sigma 10 power 4. It will be like 200 sigma. Okay? So it is clearly this sigma max is equal to 200 times. So it matches with option B. Okay. Now let us proceed. Liberty ships in World War II failed by brittle fracture due to going above the ductile-brittle transition temperature, going below the ductile-brittle transition temperature, glass superstructure, defective riveting. So the correct answer will be option B. Right, everyone? Yes, because the below dB/dt temperature, the material behaves like brittle, and above dB/dt temperature, the material is ductile. Right? So once it is going below, so it becomes brittle and it has failed. Right? The residual stresses in the interior of a tempered glass are. Right? So suppose this is a tempered glass, then what happens? How do we do this tempering? So we make this glass and in the hot condition we put air, we supply air at the top surface, right? So this cools. So once this cools, it tries to contract and it contracts freely because in the middle the temperature is still high because it has less thermal conductivity, so temperature is still high, right? Now what happens when inside of this this glass tries to solidify, it again tries to contract, right? So it tries to contract, but since this is a thing which has already been transformed to a solid, so it does not allow this contraction. So that's why here in the middle it is a tensile stress which is over there, and in the outside it is compressive. Right, so this also makes this silicate glass very tough, right? So from here you can see it is tensile. Interior, in the interior it is asked. Okay, let us move. An ion exchange method of strengthening will be effective for a sodium silicate glass. Sodium silicate, right? So sodium is there, right? So to make this one effective, so what we have to do, we have to replace this sodium with some cation which has got higher size than the sodium, right? So now you see it is LiNO3, so lithium size is smaller, NaNO3, so sodium size is similar to that, so this is also not going to work. KNO3, this K plus, so K plus size is greater. So this can be used and it will be effective, right? So option C is the correct one. Let us move. Tick the methods that improve fatigue resistance of materials. So which method improve the fatigue resistance of material? C. It is fine grain size, short pinning, polishing the surface, decarburizing. The fine grain size, it improves the fatigue, right? Because it once we get this finer size, suppose we get finer size, then what happens? Suppose there is a crack, so the length of the crack is restricted by the grain boundary, right? Then short pinning. So short pinning produces this compressive stress. It produces compressive stress which helps to improve fatigue resistance, right? Then polishing the sample. Yes, when we do the polishing, the surface cracks and scratches get removed and it does not allow the crack to propagate from the surface. So it is very good. Decarburizing is still no. Once we do decarburizing, then the strength of that upper part decreases, right? So this is not the correct one. So A, B, and C. So this is type of MSQ, multiple select question. Okay. The fatigue strength of mild steel is equal to its tensile strength, more than its tensile strength, equal to its lower than it. So yes, this lower than its yield strength. Okay. So hope guys this will help you for your great get preparation